And so we go to Laplace transform. We start Laplace transform. We have about 10 minutes to do that. Okay. This is the next transform that we use, integral transform. So we've done with the Fourier transform. Now the Laplace transform. The definition is similar, but there's some difference. So so if you have a function f, and we do a Laplace transform of that, and we define it as notation-wise. We said that this is capital F. The transform is little f, and the variable we said is depends on s. That's the choice of the textbook. Many textbooks use the variable p. It doesn't matter. Just a variable. And it's defined as integrating into e to the minus st dt. Right. So that is the definition of the password. This formally this definition, and this is integrated along real t, obviously, and then for most cases you require the function infinity of t, so that can be guaranteed for large enough s. I mean, even s is not negative, if f is falling off fast enough that you can keep a negative, even a positive s. If it exponentially small, faster than this growth of negative s. But usually we'll keep s as positive for a general function. But there's some other discussion in textbook on the property of this definition, like uniqueness, and then the usual algebraic rule, like you add the two functions, you just Laplace transform, you also add multiply constant, that kind of thing. Okay, so now once you have this definition, the next thing is just substitute a different elementary function here and see what the transforms are. So that kind of straightforward. So the first case is just f(1), which is trivial. So the fs in this case is just 0 to infinity minus st dt, but you know how to do it, right? So straightforward. 1 over minus se st the infinity. At infinity is 0. At 0 is this is 1, but it's negative, so it's 1 over s. Okay, straightforward. And the next one is so, which is similar to this one, except that you shift the argument a little bit. So it's the minus s here, minus s minus t dt. Right? So everything is the same as this one, except that s changed to s minus k. Right? Yeah. You get it? Oh, no, guys. Sorry. F is k times t, not s, k times t. I know you're confusing. Sometimes I write it too fast. Okay, k times t. All right, the next one, cos kt. Now this one is similar exponential function. This cos is 1/2 e to t, plus e to the minus kt, right? And now you use the property that I just mentioned. You can term by term, doing the term by term Laplace transform, and add the Laplace transform up and multiply the constant also. So this implied fs is just using the same. So you already know that this this term is just this one. So you first keep the 1/2 factor. This one is the Laplace transform. This one is just this one. And the Laplace transform is this one. Is this one changing k to minus k. It's S plus k. And you can simplify that also by taking the common denominator. The common denominator is product of two is s squared minus k squared. And the numerator is s plus k plus s minus k is cancelled k, and you have factor of 2s and cancel 2 s divided by s minus k squared. Okay, so that is cos, and sinc is similar. It's this thing, this the second term to the negative sign. So f is the same. The first term is the same. The second term changes to a negative sign. Now the simplification is the numerator s plus k minus s plus k. So cancel s and you have 2k. So that becomes right. Click forward. And the next one is cosine kt. Now it's very similar to cos, because now you just change k to ik. Right. So fs. So the final result, change k to minus k, that becomes s squared plus k squared in the denominator. S squared plus k squared. Right. I'm getting to it. Hopefully, you see that. Sine is again to the same, but and afterwards you just need the I, change the divided by I, right? Ik minus E, right? That's sine. So basically, it's just k changed to ik. So you have I here, but you divide it by I, so you cancel the I anyway. This is this k divided by s squared plus k squared. It's okay. So I think we're up to all these elementary functions. Now this the power. Let's continue. Okay. The next one is power. So t to n. So f is f equals to t to the power n. The fs is space. It's just by the definition. This one is slightly more complicated. T to n, especially if n is not an integer. If f is not in the integer, you probably haven't seen it, because we are doing our order, not the original order. And now you can just need to trust our definitely we can jump to the definition of this gamma function. That is in chapter 13. The gamma function. This is the last one. The definition is written in. Yeah, there's a few different definitions. But the definition that is relevant to us is 13.5. It's defined as integrating e to the minus t minus t. You can use this definition to evaluate that. So you can see the similarities. So you have exponential function, a power function, all you need to do to get the gamma function, we define this, we call it T prime, right? Then you get the, so you need to define this as T prime, so this T prime minus divided by S. So you have S to the n power n plus 1, right? But like in order to compare that, the final result, so this as this down this following S to the n plus 1. This is a gamma function, and it right now it's just we'll have the gamma function discussion in the second semester. Not the one property of gamma function is this gamma n plus 1 is just for integer n, it's just n factorial. So n integer is n factorial. Right, and that's just part of property. That's equation 13.4. That's one property of gamma function, right? So, and you for this integer case, you can also go back to here and do integration by part. Repeat the integration by part each time you reduce it by a factor of by a factor of 1. You keep doing integration by part and get to this. Right? I think that's the. I know that's one more. I don't think I have time. Yeah, right on time. Oh, we finished this discussion. More example, and because it's changed the notation. Now you're using a function u. I mean, previously it's called capital F. I'm serious about what the textbook notation. So this is a step function. So it's 0. T. Let's take K. Let K. 1 for greater than K. And there's a ambiguity at exactly T equal K, but usually we just not care too much about it. So this is the function. This is T, and at K is 0, come up to 1. Right? That is the step function. And sometimes we define the midpoint as at exactly T equal K as the midpoint. That's not exactly important for us because we are doing integral anyway. And at the just a single jump at the isolated point is not will not result in the any change in the integral. So now the Laplace transform of this u, we just follow the definition for CD3D. That is S T U K, right? And that we apply this. Obviously, K should be C. K. That's why K is positive. I mean, if K is not positive, it just means you integrate from the integrate by 1. That's the same as the Laplace transform. So assuming K is positive, so you just like integrating K into and the answer should be straightforward. So it's 1 minus S. S3 in here. And now that is just easy there. Minus S. Okay. Right? Yeah. All right. So pretty straightforward. And then the next one is combining two step function become a head function. So this F. This F D is a UT. So UT is just the same function. It's just 0 for t, negative t, and 1 for positivity. So for our purpose, calculating Laplace transform is exactly just like 1 because we integrate all the positive t anyway. So this is just like 1. Okay. You subtract by this u. This is like if this is 0, this is k. So this one will give you a jump to 1. But then you subtract by another step function that start at k. You subtract this one. Okay. With this one, subtract this one, you get your head. Right? The head function. Right. So this is the Laplace transform of this one. So we're going to do Laplace transform of this one. Laplace transform, which is do it term by term and the coefficient a. And the first one you know that, right? So that's the first one we did was just 1 over s, right? And minus this one. So nothing special. Okay, so yeah. F is defined as this one. I just write Laplace transform instead of writing another equation. I take the Laplace transform of this function, Laplace transform of this function. This is a head function defined as this one. Okay. And that one I just used what we learned before, the first example. And then this is just the Laplace transform of second term. It's this one. Right? You see that? So we first did that, this one, the Laplace transform of this function is this one, which is just the second term in this function. Okay, so I just copy it here. Is it okay? Okay, yeah, sorry. So these of 0. Let's t sub 0 is the k. K is t sub 0. It's just forget about it. It's okay. I think the final one, the last one, is just a delta function. Now we can just start over again. Just Laplace transform of a delta function v minus t sub 0. Let's substitute in the definition. Which should be trivial. Yeah, answer should be this t sub 0. Okay. Yeah, I think this is the last one, except the last equation is setting t sub 0 to 0. By this, obviously, we set t sub 0 to 0 is 1. But you go back to the integral, there's ambiguity that you integrate start from 0. So there's ambiguity. So that usually defined by convention. Whether your delta function is slightly, or your integral actually slightly less than 0, integrate with slight negative to negative 0 to infinity. Now it depends on the convention. I think your textbook is saying that the convention is include even at t equals 0, you include the whole delta function in the integral, and this it means that this equation is valid even for t sub 0 is 0. You can in that case it becomes 1. Right? And that is by I think it's just by convention. And but then usually when you encounter this kind of problem, you just need to be a little careful. You have a delta function and integrate over limit that is exactly the value that the argument of delta function is 0. So that is that could be a complication, but just need to be careful.
So what if it's not in the integral. So if it's positive 0 to infinity, so is it like undefined?
So if t0 is negative,
If the delta function t0 is not included in the integral, like
you can, I mean, that now another convention would be just keeping half. So you have basically you have integral. So your delta function is along t. If there's a delta function in the integral, so you can define your delta function. So this is delta t would be symmetric with respect to the argument. So you integrate from 0 to infinity, that will give you half. Another convention, we just I include just half of the delta function and give you 1/2. And so according to that discussion in the textbook, just basically you define your Laplace transform with instead of starting from exactly 0, you start with 0 minus a little bit smaller than 0, then you include the whole delta function. All right, that's all the example.